At this point, we know how to integrate a function of one variable over an interval, or a function of two variables over some region in the plane, what we want to do now is figure out how to take a function of three variables, so some f of x, y, z, and some region in three-dimensional space, which we'll call e, and find an integral of this function over that region. This, of course, will be a triple integral, just sticking with the same kind of notation here. That's what we want to develop in this section. And it's actually going to be not too much different from how we developed the double integral. Except this time we cannot view this as an area or a volume because the equivalent, thinking of a function over a region in three-dimensional space, would be a fourth-dimensional object. I mean, you can view this as a fourth-dimensional volume, but being able to picture that is not going to be possible. So again, we are going to start with a box, sort of like how we started with rectangles before. So we're going to have some box that we'll call B. Maybe I'll make this a little bit smaller. Why did that curve that? Oh well. So we have this box we'll call B. B is going to be a product. So here the x values can vary from A to B. The y values can vary from C to D. And I guess because we don't want to use E for one of our limits here, the book chooses R to S, even though I don't really like them using R there either. So Z values are going from R to S, Y values are going from C to D, then X values are going from A to B. We can also write this as and Z is going from R to S. There we go. So we want to integrate a function. We'll just call the function f here. That's not actually really too important for now. We want to integrate the function over this box. Of course, the very first thing we're going to do is divide our box into a bunch of sub-boxes. So we essentially divide up our interval from A to B into a bunch of little subregions. Same thing with the C to D. And then the same thing with R to S. And my drawing is going to be a little off, but that's not really too important here. We've cut up our box into lots of little sub-boxes. We're going to say the box Bij, because we have three different intervals that we are dividing up into pieces. We need three indices here. This will be the product of three different intervals like we had up here. We'll say the x's are going from xi minus 1 to xi. Y's are going from yj minus 1 to yj. And then z's are going from zk minus 1 to zk. On this sub-box, we'll pick a sample point. We'll just call this the point xijk star, yijk star, and zijk star. And the volume of this box, we're going to call this delta V, or if we want to be very specific, we can call it delta Vijk. If we want to say it's the volume of the box B. This is going to be the product. You can say delta X or delta Xi, if we want to specify it's the ith one here, times delta Yj times delta Zk. Because obviously the volume of a box is just the product of the three dimensions of the box. This allows us to set up a Riemann sum. So we're just going to take a sum over all the I values, the j values, and the k values. Just adding up all the different boxes here, but we have to go over each of the three indices. We're going to take our sample point and plug it into our function. So we'll have f of that point and then we'll multiply by this volume, which we could either write as delta Vijk, which is what we're going to do here, or we could actually even put in these side lengths. What we're essentially doing there is every little sub box is being scaled by whatever the value of the function is at a sample point in there, and then we're adding up all the results. In that way, we're essentially adding up the values of the function across this entire bigger box. Of course, in general, this is going to be different depending on how we actually set up our divisions into sub boxes. But as we let those sub boxes go to zero, the size of those go to zero, we will get the same result. And that limit, as we let those boxes go to zero, is what we're going to call the triple integral of our function f over this box b. It's basically the exact same way we define the double integral, except now we're using 3 variables instead of 2. In fact, it's exactly how we define the original integral as a Riemann sum. So we're not really doing anything brand new here, but we are doing this in a new context. Of course, we don't want to have to evaluate our triple integrals as Riemann sums. We never really want to look at Riemann sums if we can help it. We just use those for our definitions. So the first thing that we're going to do is essentially turn this immediately into an iterated integral. Since our x's are going from a to b, our y's are going from c to d, and our z's are going from r to s, we can just take that function of 3 variables, integrate it one after another with respect to each of those 3 variables across those intervals. It's just pretty much that easy, as long as we're dealing with a box. If we're dealing with a more general region, that's going to we're going to have to be a little more careful about how we set this up. Now, of course, they've written this here in the order of dx, dy, dz. We do not have to do that order. Just like with double integrals, we could do dx, dy, or dy, dx. For 3 variables, we actually have 6 different orders. Dx, dy, dz. We could do dx, dz, dy, dy, dx, dz, dy, dz, dx, and 2 more. Any of these 6 different orderings of x, y, and z is going to give you the same result, though it will turn out that some orderings may be easier to do than other ones in certain situations. So again, just like we did with double integrals, we're just going to have to try things out and see what works easiest. Of course, when we do get into more general regions, we're going to have to be a little bit more careful than that. Not every one of them can be really set up in any given order, we're going to have to figure out what orders would be best. In fact, let's actually take a look at general regions right away. So let's say we have some region in three-dimensional space. We'll call it E. We want to take the triple integral over E of some function, and we want to figure out exactly what that even means. We don't have a definition for that quite yet. But we're not going to be integrating over anything that's not a bounded domain. Bounded here meaning that there is some box that contains E. We can contain it inside of some finite box. So E is right inside there. We'll call that box B like we were doing before. We can define a brand new function. We'll call it capital F of x, y, z. This function will either be equal to little f as long as our point is in E. But if our point is not in E, or we want this to be on B, let me write it this way. So if we're inside the box but we're not inside E, we're just going to define capital F to just be 0. This is a brand new function. It has enough continuity properties as long as little f has enough continuity properties, and the region E is not too badly behaved. There's actually a number of continuity conditions that we're kind of glossing over here because they're not really going to be too important to anything that we're going to be doing with these things. But since we have nice enough continuity conditions, we can just go ahead and use this function to define our triple integral. So the triple integral of little f over this general region E is just going to be the triple integral of big F over the box. And that's just being able to define our triple integral. We're not going to actually do that to actually compute these integrals. We're going to have to come up with a better way of doing it. And just like with double integrals, we're going to need to consider different cases. In our first case, and probably the most common case that we'll come across, our region E is going to be set up as the region between two functions of x and y. So we have some, you could say, some top surface, some bottom surface, and then we just look at all the points between those two surfaces. So here, I made it look kind of like a box, but we're talking about a little bit more general than that. So this is the set of points x, y, z, where x and y are going to be in some region of the plane. So down here we have some region in the plane. And then the z values are between two functions. The book is using u1 of x and y and u2 of x and y. So we can express our function, our region, as being between two functions x and y. We're going to call this a type 1 region. Let's actually look at an example of this in GeoGebra. I'm going to take two functions of two variables. So we're going to say, let's say u1 of x and y is this going to be x plus 1. So we get some plane sitting in here. u2 of x and y is going to be x squared plus y squared plus 2. So we have two surfaces. We're going to consider some region between these two surfaces. Of course, we want it to be bounded, so we need to pick some domain of the xy plane and only look at the points between those two surfaces that are in that are over that region. So I'm going to go ahead and just pick the unit disk. So x squared plus y squared equals 1 is the boundary of that. It'll graph that as a cylinder. Maybe we'll give these different colors. So I gave them lighter colors and different ones. If we zoom in here, we're looking at the region in three-dimensional space that's inside the cylinder but between the two surfaces. So we kind of have the cylinder cut off at an ellipse down here, and up here we kind of have an indentation instead of an actual flat cutoff. But we have this region inside of here, and we might say that we're trying to integrate some function over that region. But this would be a type 1 region because it is bounded between two surfaces and then over some region in the xy plane. Now, one way to view integrals is that we're essentially adding up the values of the function, but just taking into account that we don't want to just add everything up and get infinity. It's a way of adding a continuous function of values without getting infinity out of it. And so that's the way we're going to kind of think about this in order to construct our formula. So essentially, we want to take all the values of our function over this entire region in here and add them all up. But let's maybe just take part of the region and look at what happens if we add up that part of it. And then we'll worry about putting all the parts together. Specifically, what I'm going to do here is I'm going to look at a part where I'm going to fix my x and y values. So specifically, I'm going to go ahead and pick the point 1/2, 1/2, because, or really we could say 1/2, 1/2, 0. That's going to be a point that's in our domain down here. It's a little hard to see that, but it is definitely inside the cylinder on the base xy plane. If we consider the vertical line that goes through that point, so I'm going to start with A and then just make a vertical line that goes through there. In fact, I'm going to make that a little darker so you can see it a little bit better. So that line, that vertical line, goes straight up through our region. And that is part of our region. In fact, we could view this entire region as being a bunch of vertical line segments, just all next to each other. Of course, we're only looking at the part that's inside the region, so from, say, around here to around here. In fact, we can put in the intersection points of that vertical line with the two surfaces. So we're only looking at the portion of that vertical line from this point to that point. Now, if we wanted to add up all the possible points inside this region, add up all the different values of the function across this entire region, what we could do is we can consider what is the sum of all the values of the function over this vertical line. And then we can do that for every other vertical line in the region. Well, what is that sum? Well, we're essentially just looking at the integral of f of x, y, z with respect to z. We're treating x and y as fixed values. In fact, let's even just go ahead and replace them with the 1/2, 1/2 that I was saying before. This is a function of one variable now, because we've fixed x and y to be something specific. Then we look at what points we're going from. So we're going from this point to that point. Well, that bottom point is u1 of 1/2, 1/2. That top point is u2 of 1/2, 1/2. This would be the sum of all the values of f across that line. If we generalize this, instead of 1/2, 1/2, we just go ahead and put x and y. So we have from u1 of xy to u2 of xy. We're still not treating x and y as variables right now. We're just treating them as unknowns. We're still integrating with respect to z. And that gives us the sum of all the points, all the values of the function across each of the vertical lines that go through our region. Now, if we want to add up all those vertical lines, put them all back together, what we can essentially do is integrate this function. So this is going to be a function of x and y because it's going to depend on what x and y are, what that point is. And that point varies across our domain down here. That D that we have in our drawing here. So we can integrate this function of the two variables x and y over D. And that's what we're going to get for our triple integral. Our triple integral of f over e is this single integral with respect to z from u1 of xy to u2 of xy, and then that result is we take in the double integral over d. And then we have to figure out exactly how we want to treat d as maybe a type 1 or type 2 or any of those kind of forms. In fact, we can actually be a little bit more specific about e if we want to view the different possibilities for d. Depending on the structure of d, we can actually split this up into two parts. So if d is type 1, then instead of just putting that the point x, y is in d, we know that y is between two functions of x. Here they put g1 to g2, and then x goes over some interval. So the double integral can be replaced by the integral from a to b, integral from g1 to g2, dy dx. And we end up with an iterated integral where all the limits depend on what variables are going to be left over after you go past that integral. If d is type 2, then that means that x is between two functions of y, whereas y is just going over some interval. And we do the exact same kind of thing. And this just gives us a way to build up our integral using what we already know from our double integrals. In fact, we could go a little bit further than this. Instead of using type 1 or type 2, we could also even view d using polar coordinates. And we're actually going to do that for some of our examples in this section, and we'll even discuss that more in the next section. In fact, the whole next section is really mostly about that kind of possibility and make it a little bit more formalized. For type 1 regions, we treated z as a function of x and y. There's no reason why we have to do it in that order. We could view x as a function of y and z. So if we bound our region E between two functions of y and z, we have what we call a type 2 region. If we treat y as a function of x and z, then we get a type 3 region. And we do this exact same kind of thing where we just integrate over whatever variable is treated as our dependent variable, dependent on y and z here in this case, or dependent on x and z in this case. And then we do the double integral over what region our independent variables, in this context at least, of y and z are. And so y and z are independent of what x is, but x depends on them, and we allow y and z to vary over d. Same thing here. So the main thing here is not necessarily which number corresponds to which variable. In fact, if we were trying to just number them, we'd probably start with x being 1, y being 2, and then z being 3. But type 1 regions are probably the more common one to run into. But the point here is that we can always do this in a different order if our region is set up to be able to do that. And obviously with the regions D here, how exactly we can set that up as either type 1 or type 2 region will depend on what E looks like in the first place as well. So by looking at these different types, we can essentially break down into any of the 6 different orderings of X, Y, and Z, but it will depend on what E looks like, whether or not we can actually do that. Hopefully this will make more sense as we go through some examples. But I'm going to put the examples in another video, just because I don't want these videos to get too long. There's a lot that we're going to cover in this section, and I want to make sure that all this is in bite-sized pieces. So I'm going to end this video here. I'll see you in the next one.